Hello everyone, this is Dr. Zach, and we are going to work on our fundamental theorem of calculus today. Make certain that you have completed your lesson preview before you continue with this video. As you worked on your lesson preview, you ran into the word proportional. So whenever you have a function that's proportional or a derivative that's proportional, that means that you want to multiply by the value of k. Now, as an aside, if you're told that things are inversely proportional, that means k divided by whatever your function or expression might be. Now, in this particular problem, you were given 2 points within the reading. So if you're going to write your points as t comma p, which is generally the way you let the independent variable be time and your dependent variable be whatever you're working with. Afterwards, you integrate and find that p is equal to your 2/3 k, t to the 3/2 plus c. Use one of your 2 points. Generally start with your initial value to find the c, and you come up with your new equation. You're still missing the variable k. Now you have that second point. Substitute in your t is 1 and your p is 600. Solve for p of t. The question was asking specifically what is p of 7. Now, although you don't always get these directions, write the equation for the population, make certain that you do write that equation before you substitute, and then make a statement. Now, notice how the answer should be stated to 3 decimal points, and if your sentence is rounding, let's say you're talking about dolphins or people or bacteria, it's okay to round as long as you have that 3 decimal approximation within your work. All right, so our first problem, we're going to determine the area bounded by y equals 2 root x minus x and y equals 0. For each one of the area problems, the first thing that you must do is sketch a graph. Now, you may or may not be using a calculator for this, but I'm going to do this without a calculator. When you substitute 0 in for y, you're going to get 0. If you substitute in 4, you get another 0. Pick a number, any number. I like the number 1. And when x is 1, you get 1. So we know that we have positive values above for this curve. All right, our next part of the graph, we want to graph y equals 0. So that, of course, is just your x-axis. Represent the region that you're finding. If you want to shade it in, that's fine. Don't shade it too effusively because I want you to think about the rectangles that you would be drawing. So the rectangle represents the height of the function, and that would be f of x is equal to 2 root x minus x. And then this blue line you can see ends at y equals 0, so if you know that that is going to be the height. Also, you're cutting on your x-axis. So when you write your area equation, that's going to be the integral from, well, where do these intersect, that purple line and red line? They intersect at 0 and 4. If you need a little bit more work on that, you can set 0 equal to 2 root x minus x and solve that equation. And you will, of course, come up with 0 and 4. So now we're putting in our 2 root x minus x. That's going to be the height of our graph, multiplied by dx because we are cutting on the x-axis. We need the antiderivative, and we'll come up with our nice little 4/3 x to the 3/2 minus 1/2 x squared. And we're going to evaluate this from 0 to 4. Now, the fundamental theorem of calculus is just substituting f at 4 minus f at 0, which you've been practicing in your homework, and you will come up with 8/3. So the area bounded by our 2 graphs is 8/3. Now, for question number 2, notice the integral got a little bit more complex. This is still an area problem. It's just not written as such. It might have some other application. So for this one, we're going to find the antiderivative, but we cannot do that until we do algebra. As you'll recall, algebra, trig identities help us figure out these functions. We're going to do division. So we have x over 2, x to the 1/3 minus x squared, over 2x to the 1/3 dx. Now this still doesn't look like any of our basic integration problems, so we can't find the antiderivative just yet. We're going to have 1/2 x to the 2/3 minus 1/2 x to the 5/3. Now once you have your 5/3, you are ready to integrate. The antiderivative of this problem comes out to be, well, you know what, let's factor out that 1/2. It's bothering me. And then the antiderivative is x to the 5/3 multiplied by the reciprocal minus x to the 8/3 multiplied by its reciprocal. And this is going to be evaluated from -8 to -1. Now these numbers might seem a little tricky, but I chose them intentionally. We're going to do our substitution. That's your fundamental theorem of calculus. And when you substitute your -1, we're going to get -3/5 plus 3/8 minus, and then we'll have 1/2, substituting in -8. That'll be 3/5 times your -8. Now think about this. I really want the 1/3 because the third root of -8 is fabulous, and then we'll have the 5 on the outside. And then when we substitute into the next part, we will have -3/8 times -8 to the 1/3 raised to the 8th power. Think of your exponents in that way, and it becomes a little bit easier to determine. So calculator, no calculator, you could simplify the problem. You get 57.113. So follow the guidelines that we've been working on for the fundamental theorem of calculus. Find your antiderivative and substitute in the values of b and a. Make certain you use your notation very carefully as you work through. All right, we have a new concept for you that uses the fundamental theorem of calculus. This is your mean value theorem for integrals. So if your function f is continuous over a closed interval, then there exists some value of c on the closed interval for which you have f of c multiplied by your b minus a. In essence, here's what we know. If you have some sort of curve, there's some value c in which you can find the area of a rectangle. So there's your b minus a multiplied by the height at some value of c. That would be the exact area under the curve that you're working with. Now the average value of your function is a little different than the mean value. If you're asked for the average value, you would take your 1 over b minus a and multiply it by the integral. So that would be, once again, the average value of your entire function over the interval. For our first example, we're going to find the average value of f of x equals cosine x on the interval 0 pi over 2. So the formula we're going to use is f of x average is equal to 1 over b minus a times the integral from a to b f of x dx. Now, when you use a formula, do not write just equals underneath because the equal signs are following what came before. Since this has an x value, that's not going to be entirely accurate. We want to know the average over the interval. So just write a new f average, get rid of the x value because the average is a number, equals 1 over your pi over 2 minus 0, the integral from 0 to pi over 2 times the cosine of x dx. So this is a numerical answer. We try not to use f of x as part of that answer set. So in our problem, the average value is going to be equal to the antiderivative multiplied by 2 over pi, and the antiderivative of the cosine, recall, is going to be your sine of x, and we're going to evaluate from 0 to pi over 2. When you substitute, you get your, using that fundamental theorem of calculus, sine of pi over 2 minus your sine of 0, and substitute, you end up with 2 over pi. So the average value over that entire function is 2 over pi. For our next problem, we're going to use the mean value theorem for our integrals to determine where f of x is going to be equal to the average value. Well, the average value, so we have f of c, that's what we're looking for, times b minus a is equal to the integral a over b times f of x dx. We know that f at c has to be equal to the average value that we found in the previous problem, which is your 2 over pi. So take your cosine of x, set it equal to 2 over pi, and what do we know? We know that x is equal to the cosine inverse of 2 over pi. If you need a decimal approximation, that's going to be 0.881. And from the mean value theorem for integrals, we can make the statement f at 0.881 is going to be equal to 2 over pi on the interval 0, pi over 2. When we're looking at example 5, notice we're looking for the integral, or the area under the curve of our nice little quadratic function. So it's not quite as nice as our linear problem. So think about what the graph looks like. If you were to graph this problem, it's always nice to know your zeros. You're going to have x minus 3 times x minus 1. So you have zeros at 1 and at 3. Your graph originally would have just been a nice little quadratic function. However, the absolute value makes the graph bounce upward. There we go. So that's truly what your function is. And you know that you have zeros at 1 and 3. When you rewrite your problem, you would rewrite this as the integral from 0 to 1. Now notice you're using the original function for the first part of the problem. And the original function is your x squared minus 4x plus 3 dx. Plus, now the next part of the function that you're going to look at is the part that bounced up. So it's actually the opposite sign of what we are working with. So we're going to go from 0 to 3, and we want the negative value of x squared minus 4x plus 3, and here's your dx. And then for that third part, we're going to use the original function again. We're going to go from 3 to 4 of x squared minus 4x plus 3 dx. All right, now we need some antiderivatives. And that's a pain, but let's find it anyway. If we find the antiderivative, capital F of x, for this, each one of these pieces would be x cubed over 3 minus 2x squared and plus 3x, plus some sort of c, of course. So let's think about what we'll get for each of these pieces put together. The antiderivative is going to be capital F at 1 minus capital F at 0. Minus the quantity capital F at 3 minus capital F at 0. Then you're going to have plus capital F at 4 minus capital F at 3. So all sorts of things happening here. And when you simplify, let's see here. Notice that your F at zeros do cancel out with the signs. You notice also that the F at 3's did not cancel out. So you have F at 1 minus 2, F at 3, plus F at 4. Now all we have to do is figure out these values. F at 1 is going to be equal to, well, when you're all done with everything, you're going to end up with 4. And recall, the C does not matter in this problem. All right, so when we look at example 6, notice that this does not follow any of your rules for antiderivatives because you don't have very many rules. You know your power rule, you know the antiderivative of a constant. What else do we know? We know about 6 derivatives of 6 trig functions. So Think about what you do know. You know geometry. So we're going to use geometry once again to figure out the answer to this area problem. Draw a picture. So if you want to draw a picture of this, notice it's a semicircle. Again, the top part of the semicircle, because it's positive, it's the bottom part if you have a negative. So we have the positive part. The radius of our circle is going to be 3, so we're going from -3 to 3. The directions, say, on your integrand, we're really only interested in what's happening between 0 and 3. So look at that shape. That is a quarter of a circle. So then we know that we want 1/3, a quarter of the area of a circle where your radius is equal to 3. So we get 1/12 pi times 9, and you can simplify that. So don't forget, integration includes geometry. And now the definite integral is the rate of change of a quantity f of x. And it gives your total change or net change. Net change means that it includes positive and negative values as you integrate. So your net change is the integral from one endpoint to another of some rate of change, and you use your fundamental theorem of calculus to determine those answers. So of course this is great for velocity problems. Displacement is net change. You started at one point, you ended at another point, and sometimes you have to add areas, subtract areas in order to find your net change. Now if you want the total distance traveled, that's different than displacement. You want the absolute value of the velocity to find total distance using integration. So our next example involves rates of change and integration. So a chemical is flowing into a storage tank at a rate measured in liters per minute. We're going to use units to explain why this given equation will determine the amount of chemical that flows into the tank. So if we take liters per minute and multiply by the number of minutes, what we'll end up with is an amount, or liters, which is very useful when we integrate. So if we integrate a rate, that being 180 minus 3 plus 3t, and multiply it by dt. Remember, this is now liters per minute multiplied by minutes. We're going to end up with the amount of a liquid, and in this case that would be the liters of chemical. And if we integrate from 0 to 20, all right, so next I'd like us to use our calculators to evaluate integrals. Your calculator will do that for us. So get your calculator out, type in y1 equals 180 plus 3t. Once you have that, the next thing I want you to do is go to your home screen, and on the home screen we're going to put an integral sign. Hit math, scroll down until you see function integral, click on that one, type in your endpoints 0 to 20. Now we want to put y1 in for the function, so go to vars, yvars, function y1. So that was vars, yvars, function y1. Hit enter, and you will see the answer to the question using your calculator. Now I'd also like to remind you that some of the problems have absolute values in them, and if you were to use your calculator in order to do those absolute value problems, that might make things a little easier for you. So the answer you came up with was 4,200 liters of chemical were going into the container. For our next example, we're going to write an equation for displacement. As you'll recall, displacement is going to be the net change for your distance or your position function. So we're going to integrate from 1 to 5 for v of t, dt. Now when you write the variables v of t, as long as it's been defined, you don't have to write down that whole equation over and over and over again. Use your calculator, practice with that, integrating, and you come up with 10 2/3 feet. For our next equation, we're going to write an equation for total distance. Now, total distance is the absolute value. So we're going to go from 1 to 5. Total distance is going to be your absolute value of your velocity. So write that in. Let your y1 equal the velocity equation you were given. Don't forget dt. And when you use your calculator to solve, you just need to type in the absolute value. You do not have to divvy the function up into parts anymore. So use your calculators to solve and evaluate these equations. As you can see, your displacement should be smaller than your total distance in this problem. All right, so we have about 30 minutes worth of lesson practice, and then you can begin your follow-up. Please recall calculator usage. Use the calculator when you cannot work by hand. And your book actually draws a little calculator next to the problems that you should be using your calculator. All right, have a nice day.